Structural uses of American hardwoods. Just to set the scene, I just wanted to talk a little bit about AHEC and who AHEC are. AHEC is the American Hardwood Export Council. It's based in Washington, DC. That's where the US headquarters are, and that's where all the administration is done from. I work mainly out of the European office based in London, and I also do work for Rod, who's based in Dubai. So he looks after Middle East, Asia, India, not Asia, Middle East, India, and also Turkey, of course. And we have John Chan. He works in Hong Kong, and he looks after Greater China, Southeast Asia. And we have Suji-san in Japan. He looks after the Japanese market. So it truly is a global association. So we are a non-profit association, so we don't buy wood, we don't sell wood. By communications, a communication platform, and innovative marketing strategies involving furniture design competitions, and also the use of timber in structural projects, we can demonstrate and provide inspiration for architects and promote what nature provides, and also give education to students like yourselves. Just talk about the range of species that we have in the North American temperate hardwood forest. There's around about 20 commercial different species that give architects, designers a wonderful range and pattern of colours, grains, textures to provide for architects, designers, engineers, etc. I'll be focusing on 3, which is American white oak, which is down here, American red oak up there, and also tulip wood in the middle. You can see from this slide that the temperate hardwood forest is largely dominated by oak. White oak 15% and American red oak 18%. 2 very important species which account for around about 1/3 of the whole temperate hardwood forest. We have a programme at the moment which is trying to promote underutilised species, mainly red oak, soft maple and cherry for furniture design, but I won't get into that now. I want to focus on mainly red oak and also tulip wood for structural purposes. So, this is a huge groundbreaking project. It goes back to around about 2000, 2002, and it's the Hopkins designed portcullis house, which is a barrel vaulted roof supported by American white oak glulam, supporting a glass roof, and it's portcullis house, which is where some of the offices for the Houses of Parliament and some of the MPs reside and do their job. So if this was in softwood, then the beams would have been much, much bigger because of the increased strength that hardwood gives. I will refer back to softwood because it's a reference point, because most constructional projects using wood is in softwood. Hardwood is more of a niche market, but it is developing, and there is more potential to use hardwoods for structural purposes and get it recognised. So that's portcullis house in American white oak. And after that project, European oak was originally specified for that project. But then they came to AHEC at the time and said, you know, what other projects, what other hardwoods have you got? So that set us thinking about American white oak. And we did lots of testing and broke lots of bits of wood to BS EN338 to get strength classes for 4 hardwoods: white oak, American ash, red oak, and tulip wood. Those were the 4 species that we chose. So the profile of properties that you need to demonstrate to get a strength class for a species is bending strength, stiffness, and density. Those are the 3 parameters that you need to define a strength class for a piece of wood, whether it's a softwood or whether it's a hardwood. What we found was very interesting. From those strength testing results, we found that white oak complies with the requirement for a strength class of D50, whereas European oak is usually classified at D40. And red oak is stronger in bending, but values for stiffness and density only allow it into strength class D40. Ash complies with the requirements for D35, but probably the most interesting one was tulip wood. So tulip wood has a strength rating of D40 in stiffness and strength, but we couldn't classify it because the density of the timber is too low. So we could not give it a strength class. So when we determine strength classes, if we look at strength classes for hardwoods, we look at a D rating for deciduous, and if it's a strength class for softwood, we look at a C rating for coniferous. Okay, so it couldn't qualify because of its density for even the lowest strength class for a hardwood of D30. But it would make the strength class, basically, it would be equivalent to C50, the highest strength class that you can get for a softwood. So we'll focus a little bit more about tulip wood, American tulip wood, Liriodendron tulipifera. In America, they call it yellow poplar. But we try and educate them because it's not actually a poplar. It's from the magnolia family, so that's why we try and differentiate it and give it the name tulip wood. Tulip wood, it would have existed in the northern temperate hardwood forest. It can grow in the northern temperate hardwoods, in the northern temperate region, but it got wiped out during the last ice age. But in the American forest, if it grows and left to grow, it will grow into the biggest and the tallest tree. And it grows very quickly. You can get a good yield from a log around about 40 to 45 years, similar to plantation grown softwoods. And it's very straight, grows very tall, and you have a long bole between branches, so you can get long, clear lengths, wide widths of wood. So going back to the strength and what we found, and compare it with softwood. Softwood usually density around about 420. Tulip was a little bit higher, 550, but you can see from the figures there that it's 3 times the strength and 3 times the stiffness. So it really does buck the trend from a point of view of strength to weight ratio. So if you have the correlation, which you usually compare with the denser the wood, the stronger it is, where you have softwood around about 400 and a rating of 20 for strength, tulip wood for a little bit more density, but not much, the actual strength is a lot higher. So we see massive potential for tulip wood as an alternative fibre to softwoods for structural use. The first project that we did in American tulip wood was for the London Design Festival, who we have a good relationship with, and it was the Sclera project back in 2008. We were working with the world famous architect David AHEC, and he came up with this design for Sclera. Essentially, it's laminated pieces of tulip wood laminated together and suspended from a tulip wood frame. That's another picture there. And that was outside the Royal Festival Hall on the South Bank near the Thames. So I just want to diverse back to softwood now. This is a statement from an architect in London who we know very well, called Andrew Waugh, from the Waugh Thistleton practice in London, and they now, as a practice, only build in timber. Cross-laminated timber, laminated veneer lumber, and also glulam. That is their drive to build in wood. And the statement there, if you had to invent a machine which gives you a renewable supply of building materials while reducing carbon levels, then it would be a tree. It's emphasising the fact that it's good to build in wood. It's our only renewable building material on the planet. So whether it's softwoods, whether it's hardwoods, it's good to build in wood. It's a good carbon capture when trees are growing with the photosynthesis process and forming cellulose and giving out oxygen. It's a very good method of building. Modern building materials such as cross-laminated timber, laminated veneer lumber and glulam have given architects, designers, structural engineers much better figures to be able to work with than if they were just working with conventional wood. So, recent developments, cross-laminated timber. Essentially, if you imagine plywood and using thin veneers and using the cross grain to make a panel, a thin panel, CLT just takes that a step forward and uses lamellas about 20mm thick to make panels either 3-ply, 60mm, 5-ply, 100mm or 7-ply. So you can make large rigid panels for floors, ceilings and walls. Estimated European CLT production, and this is in softwood because that's where the resource is. Softwoods are relatively cheap and plentiful. Back in 1995 there was about 2 or 3 processors with a capacity of 25,000 cubic meters. Back in 2018 we moved forward and we've now gone over the 1 million cubic meters mark. So it's a brilliant material to work with and is getting more and more popular as a building material and a method of building houses, low rise, even high rise. Going back to Wall Thistleton, this is the first 10-storey timber building in the UK. The infrastructure, the structural fabric of that building is all in structural CLT. It's a 9-storey timber building, cross-laminated lumber, completed in 2008. 4 carpenters assembled the structure on site at a rate of 1 story a week. So it's a very efficient, also a very efficient method of building buildings. And it's a quarter of the weight of an equivalent concrete building. And you need much less concrete for the foundations because you're supporting less weight. You take that forward a step. Again, Wall Thistleton project in Dalston Lane. This is probably the biggest CLT footprint in Europe. And the client originally wanted a 10-storey building and he wanted it made in concrete. But the problem was the site is above Eurotunnel, which comes out of St Pancras and goes round. So there was a level on a finite amount of the weight of the project could be. So instead of having a 6-storey complex that you could build in concrete, the client could have a 10-storey building built in timber. So, as I said, we saw great potential for tulip wood as a niche product, a niche timber for building CLT panels out of. So we did a project with Alex de Rijker, the London-based Dutch architect who we know very well. So for the endless stair, we made this Escher staircase structure out of small 3 laminated tulip wood panels. It was the first ever production, commercial production, of hardwood cross-laminated timber using tulip wood. And also enables to use lower grade material, because if you use lower grade material, glue it all together to make panels, then you're using the advantage of using that lower grade material rather than using the prime grades. So it enables the panels to be more cost effective. And also a very important property for CLT is that tulip wood is 3 times stiffer in what we call rolling shear, when you'll shear the glue line on the panels. So that was the first project, LDF, back in 2013. So we took that forward a step 3 years later in 2016 with Alison Brooks Architects, Sterling Prize winner, and she came up with a complex, looks quite simple, but it's very, very complex, the design for the Smile, which is essentially 12 tulip wood CLT panels, some of the biggest CLT panels made by the manufacturer Zublin in Germany. 3 side panels each side, 3 floor panels, and 3 roof panels. So using large plates, expressing their capacity means you have to turn it into a beam. Wouldn't it be fantastic to make a huge tube out of timber that has a cantilever? Not only 1 cantilever, but 2 cantilevers. So the brief was to be able to have the weight on a cantilever to have 60, 70 people at each end without it breaking. That was the size. It was 34 meters long, 3 meters high, 14 meter long panels in the middle and 10 meter long panels on the ends, all in different thicknesses according to the structure. That was some of the panels being manufactured. And that is actually on site in the quadrangle of Chelsea Arts College, next door to the Tate Gallery, which you see in the background. So the base, the floor panel, the base was 11 ply, and it sat on a CLT box. So we had to come along, get a digger, dig a hole, put the box in, and we had to put 20 tons of weight in that box to stop it rocking. So it was a huge undertaking. And you can see here, it's all fixed together by stainless steel plates on the bottom, and also when the side panels were put together. There was a number of technical constraints which we had to consider using Arup as the structural engineers. There was a huge side load, trying not to let the structure lozenge from the wind load. So we got over that by putting some supports on the top. And also, they fundamentally missed out the concept of when we want to get some people into the structure, and it's then, well, we need to put a door in. And that was a bit of an afterthought. So that produced some structural headaches about how big we can make the door without the cantilever actually snapping off. But they overcame that, and that was just on the limit as to what size aperture that they could have on the door. That's the side view, so it shows the side panel, 7 lamellas, and you can see the stainless steel plates there, all put together as you saw when we were making the box. There's about 4,000 self-tapping screws, stainless steel self-tapping screws, which kept it all together. I'm just going to show you now, if it works, hopefully. Can we get video on this? Yes. Or perhaps can we show it later? Can we get video? Sorry. It's a really good film and explains all of the project. Perfect, thank you.
For the London Design Festival 2016, AHEC have partnered with Alison Brooks Architects and Alan to create the Smile, an extraordinary American tulip wood structure displayed on the parade ground at Chelsea College of Art and Design, which showcases the potential of cross-laminated hardwood on a large scale for the very first time.
CLT has this clever way of making huge panels from small trees, but nobody has ever tried to do a hardwood CLT panel of this size and scale before. And Smile is by far the most complex project which has ever been built in CLT. So working with Alison designing this, we found it an incredibly exciting process.
We designed a pavilion that takes the form of an arc. So it's actually a really athletic structure. It's doing something that I think hasn't been done before. It's based on a 50-meter radius, it's 34 meters long, and it's actually a two-way cantilever.
We are Tim and Timber, and we are based in Bavaria, the southern part of Germany. At the moment, we are manufacturing the CLT panels. The first step in producing CLT is to have endless boards, which are cut in the lengths we need. The method we use to produce an endless board is called finger jointing. After the finger jointing, the boards are glued crosswise. Most of my project will produce panels in dimension of 40 meters in the length and 4.4 meters in the width. So it helps our expert wide and extra long. One special case here in our company is that we produce cross-laminated timber by using vacuum presses. And the pressure of a vacuum press is 800 kilograms per square meter. For the CNC machining, we have an 8-axis robot.
By machining them to 1 millimeter tolerance, it means that when you bring things like Smile to site, they fit together absolutely perfectly. One of the things that's made timber construction a lot cheaper is these long self-tapping screws. These are about 300 or 400 millimeters long. And so that is how we connect the CLT panels and the Smile together. And it's because those screws are going with tulip wood, so those screws are 20 or 30% stronger than they would be if we were fixing into spruce. It was really only by using the tulip wood that we were actually able to get something which was strong enough to carry those stresses really above and below the door to stop those cantilevers snapping off. We're looking at up to 10 tons of force from the wind, trying to make the whole cross-section lozenge. So all the forces from the people, 60 people at one end, all the force from the wind trying to rotate over, all of this is concentrated on this tiny little area where it meets the ground. That's part of the engineering challenges that went into this.
We had the idea of introducing holes into the sides where there are the least stresses acting in the CLT. So it's a kind of graphic way of illustrating what's happening to the material itself as a structural element. The Smile is definitely pushing boundaries in the use of CLT and trying to break new ground in terms of what timber can do.
It's really thrilling to see the public interact with the structure, but also more importantly is using the data and experience and the knowledge gained in this project to feed into commercial use of hardwood CLT in the future, and that's the real legacy of the Smile.
There we go. Smile. Quite impressive, eh? These are demonstration projects which we are able to work with architects like Alistair Riker, like Alison Brooks, to show the capability and the potential for this material in construction, and then try and drive it forward commercially, because as I said before, we're not a commercial animal, but we have been able to attract 2 or 3 niche producers of CLT in Europe to the possibility of, you know, using that as a material instead of spruce for, you know, design and building in hardwood CLT for niche projects. One of those projects is Maggie's Centre in Oldham in Manchester. Very special building. It's a cancer care centre for people who have been diagnosed and are not very well. This is the schematic, the original model that Alistair Riker came up with of how he wanted the building to look like. And this is the finished building. Outside it's all clad in tulip wood, but it's thermally modified tulip wood. I won't go into that in detail now, but it enables tulip wood, which is not durable, if you modify it, to be able to use outside for cladding and facades. But the interior and the structure, the structural fabric of the building is all in Tulip Wood CLT. So it's the first commercial building using structural CLT in hardwood, which is Tulip Wood. Those are some of the panels. You notice that with the smile, the lamellas on the outside, they're always balanced. Either they're odd, like 3, 5, 7, 11. We're running horizontally because there was more layers because it needed to take more stress. Whereas these panels are just vertical panels taking a load. So they're 5 lamellas thick, 100 mil. So the outer layers 1, 3 and 5 can be vertical. There's not as much stress as being placed on a panel that was in the smile, if that makes sense. A little video of the building. It shows the inside. So all of the tulip wood panels inside have been left unfinished because they wanted the aesthetics of the tulip wood to show through. All of the handles are all in timber. And all of the ceiling of the main building is all in tulip wood strips. This project just happened to coincide and run alongside the panels which were made for the smile at the same time. So we were able to utilise some of the offcuts from the smile to be able to use it in this building here. And it's a wonderful building. A few shots of the inside. Gives this beautiful light transparency to the building, and inside you come up with this glass atrium, and inside is a silver birch tree that grows up with the tree of life. Then we moved on to probably the last project that we'll do as a design project was Multiply. Again, working for London Design Festival, we have a very close relationship with Ben Evans, the director of London Design Festival. We either do a furniture design project or we can do a structural project in September. And this was going back to 2018, where we made 108 2.7 metre square panels up in Scotland at their little vacuum press, which you see up there. That's me up there on the left. And then they were cut down at stage 1, which is in the bottom left-hand corner, on their CNC machine to make panels that could fit together with this very simple castellated effect and then bolted together. To produce Multiply, a 17-cube modular section building that was all integrated. All of the cutouts were made into stair components so that could all be linked together, so you could walk up to the very top or sometimes get lost. So that was in the Sacre Courtyard in London of the Victoria and Albert Museum. And again, the weight was constrained because that is actually a ceiling above an atrium underneath. The beauty of this is that you can transform it into different layouts. And this was the layout that we took to Milan in 2019 for Milan Design Festival. And then just before COVID, in February 2020, we were able to take it to Milan, again in another configuration, or again all integrated so you can move around in the pavilion. From that project, we were able to make some panels for testing. So we tested them at Edinburgh Napier University to get some structural data on how these panels performed structurally in flatwise bending, edgewise bending, to compare and contrast the properties of this material against published data for conventional, say, softwood published data from 2 softwood producers of CLT. And they're all in this document here, which is available on the website. And the results were very, very positive. Just want to show you another little film of how Multiply was made. Let me get this to work. Here we go.
One of the things that's been really interesting for us with this
Really
project
nice.
is to use an American hardwood to look at the different strengths and different types of timbers. For a long time we've been using different sorts of softwoods from all over the world, and now into the hardwoods and what they can do. So we stronger panels with these timbers, panels that have really specific uses. And I think that what this does is this allows us to kind of broaden our imagination in terms of the kinds of buildings we will be able to build. Tulip Wood is a hardwood that grows across the eastern side of the United States. Really fast-growing hardwood. Yellows and purples and rich brown. Really beautiful colours coming through. This is a cross-laminated timber. What that means is you run the planks perpendicular to each other in layers, so 90 degrees from the layer of planks below. And you build those layers up in about 3 or 5 layers of planks. And when you do that, what you have is you have this incredibly strong panel, because you have planks that are working in both directions. So it increases the strength of the timber massively. It also means the timber doesn't move, it doesn't warp, it doesn't expand, it doesn't contract. So it's a really stable material to work. A tree is in effect a carbon store. So by building our buildings in timber, we are building carbon stores. Now if you think about the alternatives to that, concrete, cement, steel and brick, these are massive emitters of carbon. So actually building buildings, building useful buildings from timber is a way not only of reducing climate change, but actually beginning to reverse the problem. So that's really exciting for us.
There we go. That was Andrew War, who you saw walking up, and he actually narrated that. He told the story, didn't have a script, just spoke passionately about, building buildings in wood with this slant on building in tulip wood. So that's cross-laminated timber. I want to go back now to glue-laminated timber, where again, using lamellas, but making them into structural portal beams, which can be as strong, if not stronger than steel, to make unsupported beams without any columns or anything like that. Sometimes up to 50 metres, depending on the size of the beam. These are some quite large curved beams, which I took a picture of a few years ago. Again, these are softwood. I have to go back to softwood occasionally to show the capability and the curves that you can get and how you can engineer timber to make these structural beams. This was up in Rubina, up in the top of Italy, up in near the Alps. Go back to Portcullis House, which was the pioneer project for us, really, that first opened our eyes, as I talked about at the beginning of the presentation, in laminated white oak. And also a slightly different dimension, the cigar-shaped tubular columns, again laminated in white oak and turned on a big lathe to form the initial support structure for that roof. A similar project, again going back a few years, was Hounslow East Tube Station. Not very glamorous, you might say, but the actual columns themselves, these cigar tube-like structures, again were fabricated and turned out of American white oak to produce the support structure for the softwood grid shell roof. And also these beams on the outside, again in American white oak. So we really know we have a good idea of the structural capabilities of white oak. But what about red oak, the species I mentioned at the start of the presentation, which is the most abundant species in the American hardwood forest? It's often seen, particularly in Europe, as like the poor oak species, and we're trying to rectify that with some projects that we're doing in furniture and also in structure. This is American red oak. Wow, you might say. That's a project that we did called the Timber Wave. Again, it's by Amanda Levitt, ALA Architects, based in London. A hugely complex wave made out of American red oak. And all these components are almost individual and different. It was put together in 6 units and then taken to site, and then they all had to fit on site. There was no trying it out beforehand, they all had to fit. And amazingly, they did. So this was made from 3mm lamellas. So the thinner the lamella, then the more intricate you can be with curves and designs. And that's a close-up of the timber. Some other commercial projects. This is King's College School in Wimbledon in London, and this is a hybrid. So this is an example of, depending on budget constraints, sometimes it's project, it's money, no question, doesn't matter how much money you want to throw at a project. Others, you need to be more constrictive in the materials that you use. So this was made by Hess, fabricated by a company called Hess in Germany, and it's a white oak spruce hybrid. So essentially the core of the beams, which you see on the ceiling, the core of the beam is spruce, but it's actually clad to get the aesthetics and the appeal of the American white oak. So again, you can have a compromise between the two. You don't have to have straight softwood, you don't have to have straight hardwood. Sometimes you can compromise and use the two materials together to form this wonderful roof. Then we have, for those of you sporting people who know cricket, the game that we play and love in the UK. This is the new Warner Stand, which is part of the redevelopment of the Lord's Cricket Ground. And the architect, who was Populous, wanted to go back to timber and have timber as the supporting structure of the roof. So, after a lot of research, he settled on utilising American white oak. Again, European oak was considered, but because of the better strength class of American white oak and the straighter grain of American white oak, they went with that species. So we have 11 of the biggest cantilever beams in Europe. The cantilever actually sits on the stanchion and is 12 metres back, connected to the wall, and then the 12-metre cantilever sits out under the canopy supporting the roof. They are 300 millimetres deep at the deepest point where it sits on the stanchion on the support. Sorry, a metre deep, 300 millimetres wide, and each weighs about 4 tonnes. Huge structure. When I was there, when they were installing some of the beams, I said, how much tolerance is there when that sits on there? And he said, there is no tolerance, nothing. It has to fit. And it did. So there we go. That's the finished stand. 11 cantilever beams, all in American white oak. This is one I took at the factory, where I said, we don't take any photographs, please, but I managed to get these two of the manufacturing process just before they were CNC'd into the final shape. Just going back now to tall buildings and what you can build now in wood. I'm not the best advocate in having to build the tallest structure and the tallest building. I think timber is very good for low to medium rise, say 5-6 stories, perhaps 10 maximum, as we saw, 9 stories, 10 stories we saw with Murray Grove. This is in Norway, and it's actually about, I think it's 83 metres tall. It's quite phenomenal. Using huge glulam beams like that to support the structure to get the rigidity that you need in the building like that. But that's where we are now. That's what the sort of buildings that can be built in timber. Lastly, this is quite a recent project, isn't it, Rod? In South Africa, and it's in white oak again. It's not laminated, but it is steam bent. Some of the components are steam bent to get some of the structure and the shape. And it's the Bahçeşehir wine estates in South Africa. So some's internal, some is using the natural durability of white oak for external. It's a very interesting and complicated structure. And I'll just finish with this slide, which says, timber is the new concrete. And it's from our good friend, Alex de Rijker. So there we go. And you can follow us on Twitter, lots of great information on the website and on Instagram. So that's the end of the presentation. Thank you very much for listening. Thanks for your attention.